Good afternoon, everyone. My name is Bhargava Shastry. I'll be talking about fuzzing the Solidity compiler, which compiles the Solidity smart contract programming language into Ethereum bytecode. I work for the Etherum Foundation. A brief intro. I'm a security engineer in the Solidity team, where I mostly work on semantic testing of the Solidity compiler. My role in the team is to find security critical bugs in the compiler as soon as possible, hopefully before it is shipped to end users. Now, the threat model that we mostly work with is incorrect code generation. What that means is we do not want the compiler to generate incorrect code whose semantics is different than what is intended by the user or the developer, software programmer. To do this, what we do is we randomly generate valid Solidity programs. Yule, to be specific, Yule is, let's say, a low-level dialect of Solidity to test the compiler. And using this approach, which I'm going to describe in more detail in the coming slides, we found about 10 bugs, and we continue to use this approach to test Solidity on a regular basis. And thanks in no small part to Google's OSS Fuzz initiative, we are able to run the fuzzer on Solidity every day. So the latest code gets picked up and gets fuzzed. Okay, so let's get started. Just a few more words about the threat model as such. We assume that the compiler user or the programmer is not malicious because it's not very interesting to maybe look at inputs that crash the compiler, because compiler as a piece of software, unlike, let's say, a network server or a, let's say, protocol parser, which is deployed on an endpoint, is not as so compiler is not so sensitive to let's say being crashed in the way remote servers are crashed. So we assume that the end user is a benign user, and we mostly focus on bugs that are introduced by the optimizer, where the semantics of the code that is generated and deployed on the blockchain is different than what is intended, because that can be quite bad. I'm not sure I'll do a very good job at providing more info or a better introduction to fuzz testing than speakers before me. But just to speak about it in a nutshell, fuzz testing means continuously generating pseudorandom input and feeding it to the program under test until something happens. Either it crashes, reports a bug in some program path, or not. So in practice, it is bound in time. So you usually fuzz for a few hours every day, especially with initiatives like OSS Fuzz, but on a continuous basis, because the code under test is changing every day. Although pseudorandom input generation is great, it is limited in terms of what it can do to programs that accept highly structured input. For example, a compiler. To illustrate this, this slide on the left-hand side shows a reasonably valid Solidity program if you assume that do something is a function that's been previously defined. All the keywords in place, so on and so forth. And it's quite likely that a pseudo-random mutation of the program on the left is going to result in the insertion of garbage characters as far as Solidity grammar is concerned. So it might basically mutate the function keyword to something else, which does not make any sense to the parser, and the end result being it's going to be immediately rejected. And we don't want this, because what we are hoping to get to is the code generation phase. And to do that, we need programs that are accepted by the front end. Okay, so the main lesson here is that fuzzing, a program that accepts highly structured input, such as the Solidity compiler, requires generating valid programs. And to generate valid programs, we need some sense of grammar or structured awareness of the input that is accepted. So now I'm going to describe the approach that we take to essentially embed structured awareness and meaningfully test the code generator. Step one is we start with a specification. Previous speakers have already spoken about how important it is to use a grammar to fuzz programs that accept structured input. I fully agree with them. I cannot overemphasize this. Yeah, so having a specification definitely helps. In this slide, what we see is a specification written in protobuf language. One of the fuzzers that we use essentially makes use of the interface provided by libfuzzer, which accepts essentially protobuf input and provides a mutator for it. And protobuf is data description or data serialization language. What that means is you describe what data looks like. And for us, data is a Solidity or in specific yule program. And like any programming language input, what it consists of, for example, is a block or a basic block, which is a set of statements. So you see keywords such as repeated, message, and so on and so forth. What is important to note is that what we are essentially describing is specific structures within a yule program and how you can essentially generate them. So repeated, for example, means one or more, actually zero or more, and so on and so forth. So what you can see is that you begin with a program, a message called a program, which is the high-level program, which consists of a repeated sequence of basic blocks, and the basic blocks in turn consist of a repeated sequence of statements. Of course, this leaves out a lot of diversity in the grammar. If you want to take a look at the full spec, it's linked in the slide below it's on GitHub. So yeah, input generation itself. So we have the grammar now. Input generation itself, fortunately for us, we do not need to write an input generator because libprotobuf mutator, which is also developed by Google, interfaces with the said protobuf spec and generates trees that respect the spec. So each input can be seen as a tree, somewhat JSON syntax like. So you can see that it looks like nested braces and identifiers that identify what goes inside the nested braces. So for example, we start with blocks. That's a basic block, which contains statements. And the statement in this particular instance is an if statement, which contains a condition, which is an expression. It's actually a binary op or a binary expression, and specifically the equality binary expression, so double equals, whose left side operand is a reference to a previously declared variable whose ID is 0, and the right side operand is the constant 0. So you can essentially use this format to even, for example, encode somehow context-specific actions like reference to a variable, and so on. But more about this later. Yeah. So this is what the input looks like. But you can already notice that this input is unlike Solidity source code or in specific yule source code. So what we need, step 2, is convert the input that's generated by libprotobuf mutator into something meaningful. In other words, a yule program. For this, we write a glue program between these two components, which is conveniently called a converter because it does just that, source-to-source translation. The input to the converter is the protobuf input that is randomly generated by libprotobuf mutator, and the output is the yule program. So it's the job of the converter to essentially translate from one to the other. So as an example, a couple of slides before, I mentioned what the tree of random input generated by libprotobuf mutator looks like. It's shown on the top. On conversion, it should result in a yule fragment that looks like what the arrow is pointing down to. In other words, a simple if x equals 0. Yeah, so so this is actually quite descriptive on top to arrive at something very concise at the bottom. But you can imagine a complete tree is being a lot more verbose, leading to a more complete program. In other words, we could have things like functions, control flow statements of various types, and this if statement being embedded in a portion of the program that is generated. So in summary, this is what our input test program generation pipeline looks like. We begin with a protobuf specification of what a yule program should look like. We use libprotobuf mutator to essentially, essentially generate instances of input based on the spec. That spec can, the generated input cannot be used as it is because it doesn't make any sense to the compiler. So we use a converter which finally converts the spec or the generation of the spec to a valid test program. Okay, that's only part of the puzzle. Correctness testing requires somehow that we know what is to be expected and whether that expectation was met. In this specific instance, we need to know if what is the semantics of the original input, and does the optimized code also retain that semantics, or does it diverge? How do we do this? We use differential fuzzing. What this means is essentially we take the input that is generated by the fuzzer, which is a valid yule program. We track its side effects using an interpreter. So we had to run the original program, and then we optimize the set program by compiling it and optimizing it, and also obtain the side effects by interpreting it. And finally, we compare the side effects of the pair, so the original unoptimized program and the optimized version of the same program. They have to be identical, otherwise it most likely means that there has been an optimization done that essentially changes the semantics, and that's a bug in the optimizer, which we want to find as soon as possible. So to precisely do this, to actually track the side effects, we have the yule interpreter. It's an interpreter which accepts yule source code and essentially outputs a side effect as a trace, which is a sequence of strings which describe change to the state. For example, memory being written to some location, or storage being written to some location. So in summary, each test program that is generated by the fuzzing pipeline is interpreted and an execution trace obtained. So what this means is that our pipeline looks like what is shown in this slide. Each iteration generates a random program that is optimized, and the pair of unoptimized and optimized programs are interpreted. The traces are obtained, and we compare these traces for equality. They're mostly equal. If they're not equal, it's most likely a bug in the optimizer. More recently, we've been experimenting with custom fuzz mutator. I mentioned earlier that fortunately, we don't need to worry about input generation because libprotobuf mutator is already capable of generating protobuf input. But we've found that there are deficiencies with the purely entirely random input generation. It's simply because as someone, domain knowledge is important, and encoding this domain knowledge pays off. So custom mutations pay off. So things like making it easy to flip conditions, like change an if condition to a negation of the condition, can be useful. But in practice, what is useful is generating programs that specifically test specific optimization phases. So for example, if an optimization phase is removing dead code, a specific mutation that could help for this testing this phase is to generate dead code, right? And it's unlikely that the random mutator is going to generate dead code by itself efficiently. So now we come to what we found using this approach. We found about 10 bugs, 3 in the optimizer rule. The optimizer rule is essentially a rule which states the transformation that should take place. For example, if multiplication between 2 operands, one operand being 0, should result in the product being 0. So any multiplication with one of the operands 0 must be necessarily optimized to a constant 0, stuff like that. I'm not saying that bugs were found exactly in this, but just to give you an idea what an optimization rule looks like. So it turned out that 3 of the times the optimization rule was buggy in corner cases. And in 7 of the instances, there was a bug in the yule optimizer. This is the new version of the optimizer that we are working on. If you look at how many of them were post-release, pre-release, it's roughly 50-50. So the hope is that we reduce the percentage of production bugs because we want to catch most of it before it goes into production. Also, experimental here means that bug was found in a feature that's been marked as experimental. If you look at bugs by severity, 6 of them cannot be classified because they were either not enabled by default. And it was a bug in a feature that was not enabled by default. So it would have been very hard or almost not possible for the user to be affected by that. Having said that, we did find couple of low severity issues and a medium severity issue that was found by custom mutations. At the moment, we are also considering working on an antler-based custom mutator. I think a couple of earlier talks mentioned how effective it is to use a grammar-based generator than a random generator. So that's essentially where this work is pointing towards. So the goal is to essentially have the mutation or the generation create as valid a program as possible. So to just give a perspective or the context to this, I mentioned that we are using libprotobuf to test yule, which is an intermediate level representation of Solidity. But Solidity at the moment itself as a language is being tested randomly. So we want to move towards a more grammar-based approach than random approach. So this concerns fuzzing of Solidity and not yule that I previously mentioned. Okay, that brings me to the end of the talk. In conclusion, I described how we are undertaking continuous structure-aware fuzzing for early bug discovery of the Solidity compiler. It has proved to be useful in practice for testing optimizer and also data encoding and decoding that this talk didn't speak about, but we're also doing that. The assurance is pretty decent, I would say. There's evidence that it works, but of course, there are no formal guarantees because what is not found cannot be said to be a proof that there is no bug. So yeah, classic caveat supply. But yeah, it's proven to be quite useful in practice. Yeah, that brings me to the end of the presentation. I'd just like you to point you to our source code on GitHub and our GitHub channel. This is where the compiler team is active and we discuss active compiler development and stuff like that. So if you're interested in Solidity compiler interested in contributing to it. We also have bi-weekly calls on Monday and Wednesday, so feel free to say hi on the channel if you're interested. Yep. Thank you. Thank you for your time.
Thank you, Bhargava, for this interesting talk, which was new and informative to a lot of participants. So one question is, how long did it actually took you to set this framework up?
So the libfuzzer part is actually pretty straightforward. So there are multiple components. One is continuous fuzzing with OSS fuzz. That part is as simple as writing the test harness, which is pretty straightforward. Of course, if you want to randomly test it, it could take you as little as a week to set it up. But if you want to use custom mutations and grammar awareness, that can take about, I don't know, a little more, to maybe a couple of weeks or 3 weeks of programming plus another few weeks to get that right, to fine tune the mutations and stuff. So I would say a few months.
Okay, thank you. And how do you ensure semantic validity?
We ensure that by, so the essentially on a technical level, there's an assertion that fails if the input generated by the fuzzer is syntactically or syntactically invalid. So I don't know if that's what the person who asked the question means. So the glue code, the converter code that translates between a protobuf to yule code, ensures that the syntactic validity is respected. How do we test the semantics itself? We take the trace of the program that is actually run on the interpreter and check that it's equal to the optimized version. Yeah, I'm not sure if I understand what is semantic validity, but yeah, hope I answered the question. So as in a variable is not defined, I'm just reading the chat, variable is not defined but used. That cannot happen because the converter is aware of semantics. So the protobuf format is not context sensitive, but the converter that we use is. So that's how we make sure that variables that are referenced are always defined. So the converter keeps track of the state, and the state, one part of the state is checking if a variable is defined, and only then referencing a variable. Cool.
Yeah, apparently that was understood. Are there any more questions? We still have some time.
I just checked the Slack channel, and yeah, I didn't find anything. So I guess I'm just gonna wait.
And also, you can answer any questions later on if you want to.
Sure.
Yeah. Okay.
Okay, I see a question by Kostya. Any feedback for libprotobuf mutator? I guess I don't have specific. Well, one option, one feature that would be nice is to make it easier to write custom mutations, especially when one is experimenting with libprotobuf mutator and you see that a specific pattern of code is not being generated and you want to do it. Yeah, I mean, I understand that there is an interface that we are currently using, but yeah, somehow to make it more modular, and maybe I need to think a little more deeper and make an issue on GitHub. The second one is, what is the next step for you to improve your fuzzer? So what we find is that pseudo-random fuzzing, especially for solidity, is very poor. So over 90% of the time, the program generated is syntactically invalid. Another issue is that, okay, if we want to use libprotobuf to write a complete spec for Solidity, it is somewhat time consuming. We have an Antler spec now, so it's much easier to use an Antler spec to generate to write an input generator, and we don't want to like duplicate the time to replicate different grammar formats. So the next step would be to somehow use the existing grammar and generate programs which succeed more often. So bring that percentage down from 90% failure to maybe 50%. So every other program generated by the fuzzer is meaningful to the compiler. So
one more question.
Sorry?
You can select the one if you want to. There are 3 right now.
Yeah.
Sure. Okay. So are you monitoring code coverage? Yes, from time to time. Are you using differential fuzzing between compiler versions? No, not at the moment. Because yeah, it's not part of the threat model at the moment. Did you measure coverage in the compiler? How much could you cover with your fuzzer? So with grammar-aware fuzzing, it's clearly superior. So you can reach close to 100%. I would say 95% of the subsystem that's tested. Random fuzzing can be somewhat poor. So you need to support it with a dictionary of keywords and so on. How do you prioritize different custom mutations? This is somehow, let's say, unscientific and rule of thumb. Yeah, it's driven mostly by the threat model. So if we want to test a specific component of the optimizer, to use mutations that test specifically those optimization patterns. So for example, det code, generate random det code. Is differential testing done manually? No. Essentially, the test harness automatically compares the trace between optimized and unoptimized programs. Yep.
Okay, thank you, Bhargava. We're just right on time. Thank you for answering all these questions and for being part of the conference today.
Thank you. Thank you for having me. It was nice to speak and listen to the other talks. There were some really interesting talks early as well.
Yeah, there are still some interesting talks to come.
Yeah.